also really challenging to be working up to 3 jobs at the same time because I moved out of, my parents' house, and I like was living with my younger sister. We had bills to pay, and didn't qualify for student loans, so I was working a lot. So that was really, really hard. But it was really my love of astrophysics that kept me going. And there were multiple times, in fact, at these jobs that I had. One in particular stands out where the human resources person comes by and says, like, hey, you're really good at this call center job. Like, why don't you just quit your degree and start working here full time? Like, you're going to end up here anyway.
Oh,
And I
wow.
was like, no, I'm going to be an astrophysicist. And he was like, yeah, sure.
Oh, wow.
Exactly.
That's
Uh,
that's really
yeah. But, also just, I think that, if you like, that might be true for a lot of people that are doing, different kinds of degrees or something. I don't know. But I
yeah,
was like, you obviously don't know who I am.
exactly.
I'm going to be an astrophysicist, and you don't know it, but I know it. And there
Yeah.
were a few times where people were like, why are you doing this? Just like get a job. And I was like, no, I'm going to do black holes.
Welcome to Origins with Dr. Natasha Wilson, where we explore the unique origin stories from the childhoods of leaders in science, technology, engineering, arts, and mathematics, also known as STEAM. Today, I will be a conversation partner with our guest, Dr. Chiara Mingarelli. Dr. Mingarelli is a gravitational wave astrophysicist at the University of Connecticut Department of Physics and an associate research scientist at the Flatron Institute's Center for Computational Astrophysics. She was a Marie Curie International Outgoing Fellow at the California Institute of Technology and at the Max Planck Institute for Radio Astronomy. This year, she was appointed to the executive committee of NASA's Physics of the Cosmos program group and also became the 2023 Head Early Career Prize winner for her outstanding contributions to the field of gravitational waves. Other notable honors include being a runner up for the 2022 Springer Nature Inspiring Women in Science Award, being the American Physical Society's Woman Physicist of the Month, and receiving grants from the National Science Foundation, the European Research Council, and Amazon. Dr. Mingarelli also is a writer, speaker, and creator who has conducted science outreach in a myriad of ways. She has written articles for Scientific American, CNN, The Wall Street Journal, Popular Mechanics, the BBC, and more. She has also been featured on podcasts such as Sean Carroll's Mindscape and regularly contributed to a blog and YouTube channel called Smart Girls, whose motto was Change the World by Changing Yourself. In the fall of 2023, Dr. Mingarelli will be joining the Department of Physics at Yale University. We welcome Dr. Mingarelli to Origins, and we invite her to share with us the touch points of her early childhood that have led her to where she is today. Welcome, Dr. Mingarelli, to Origins, and we're happy to have you here. So, on Origins, we like to focus a little bit on childhood and especially those touch points of your childhood that brought you to where you are today. And so, if you wouldn't mind just telling us a bit about your childhood.
Yeah, it's so nice to be here. Thank you so much for the invitation, Dr. Wilson. So I grew up in Ottawa, Canada, in a small suburb called Rockland. And I was outside a lot. I loved to play outside, and I loved looking at the night sky. So my friends and I would take walks around our block, sometimes for hours and hours at a time. And we would look up at the night sky and just, wonder about the stars and what was out there and think about exploring. And that was really my thing when I was a kid. I just loved to explore and discover things. And I, thought that in the best version of my life, I would be able to explore outer space and discover new things about outer space. And when I, heard from my dad that black holes were a thing and he described them to me, he's a mathematician, I was hooked. I just couldn't believe that such, seemingly magical objects existed in nature and that one could have a career studying them. For me, I think I was 10 years old when I asked my dad, I said, I really like astronomy, but like, is there astronomy with more math in it, like astrophysics? And he was like, oh my God, yes, there's astrophysics, and you can do it. And I was like, great, okay. And then a bit later on, I was like, well, I think I should tell you that I know that you've been lying to me. And he was like, what? And I said, well, you said that I could have a career studying black holes. And he was like, yes, you can do that. And I was like, well, like if that were real, then everyone would be doing it. So obviously, like you think I'm a little kid. You can like, don't lie to me anymore. Tell me the truth. Um, so I think, today reflecting back on that, it's funny, but it's also sort of true, right? It's not necessarily true that everyone can have that vision when they're a kid and grow up to be an astrophysicist. I had a lot of privileges growing up with a father who was a professor and could guide me and, tell me that that was a possibility. I think it's so important to be able to picture your future, to have some sort of, concrete image of yourself and to be able to see role models. And that's another important thing that I had. When I was in high school, I was introduced to Professor Victoria Caspi at McGill University when she was just starting out there. And she was an amazing role model for me. She's one of the, pioneers in pulsar timing and has done really important work in the field. And I met her when I was 17 years old.
Wow.
And so I could, picture myself being a professor and doing what she did. So role models were always really important to me. And I was really lucky, I think, to have, both parents who were really invested in showing me role models and supporting my interests.
Oh, that's great. So,
Yeah.
did your love for mathematics, because you specifically said you wanted math to be involved, so did your love for
Hmm.
mathematics kind of bloom because of your relationship with your father and his profession in mathematics?
It's hard to say. I think so. There's not another version of the universe where I can compare, like what would happen if we didn't. But I think it was always a part of it. My father loves math so much that I always found it to be very infectious. But at the same time, I have six siblings. I'm number two of seven children. And my youngest sister is also a scientist, but she's studying biology. So I was the only one that really kind of got hooked into math. And so whatever it was, like whatever that spark was that my dad had that he saw in math, like I also have it. But for me, it just manifests in a slightly different way. I, project that onto space and black holes and my childhood and the night skies full of stars.
That's amazing. So, I used to love looking out at the stars, and one of my favorite things to do in the world is go to the planetarium, or at least when I was a kid, it was. So
Yes.
I lived kind of in the suburbs, so I experienced a lot of light pollution. But it sounds like maybe you didn't have as much light pollution, so you were actually able to see a full sky of stars at night.
Yes, there was almost no light pollution at all. And of course, we complained very loudly about it because we thought that that meant that we lived at like the ends of the earth and like our little development was really kind of on the very outskirts of this suburb. And so it was a new development and there was really nothing around. But I think it's the biggest stroke of good luck I think that I ever had. I, have so many memories of looking up at the moon and just staring at it and then realizing that the first star that I saw at night wasn't even a star, it was Venus, and all of these little things, and then the red dot was Mars. And you know I loved picking out constellations and just kind of dreaming about traveling to them. And I also remember a really influential part of my childhood was discovering the speed of light and that the light leaving the stars, you know arriving now left, potentially thousands of years ago, maybe even longer. And
Mm.
that there's like time travel that's inherently happening from, the time that that photon left the star and traveled tens of thousands of years and then like hit my eye so that I could see it. Like that's bonkers. That totally,
Yeah,
totally blew my mind. It
yeah,
still does. I mean, that's like those little photons just for me, like hitting my eye, and then like you can see that star. Like what? But like that's space. It's incredible.
It is incredible. The size, the magnitude of space is absolutely
Yeah.
incredible. Yeah. So, you mentioned a bit about who you looked up to when you were young. So what was school like for you, especially having kind of a fascination with black holes? Were there like maybe talk a little bit about the classes maybe you ended up enjoying, and then maybe also how you interacted with your peers, maybe?
Yeah, I feel from the way that you're asking the questions that you know the answers.
Well, you never know. You might have went to a school full of black hole lovers.
No, I went to Rockland District High School, and it was a public high school, and there were no black hole lovers. There were no black hole haters, so that's good.
That's good.
But yeah, school was always it was challenging for me in a lot of in social ways. I really prided myself on being very good at school. And I thought that everyone should, also be very happy that I was doing so well at school. But my classmates thought that that just kind of made me a super nerd. And, so it was socially difficult for me when I was a kid. And there's a few times that I didn't go out at recess and I stayed in and I read the dictionary.
So,
um, but, I loved reading the dictionary. I thought it was fun. And I also had Encyclopedia Britannica back in the day. And I would also like go through that because it was just like all of this knowledge right there. It was like Wikipedia printed, right? And you could just like go through it for those of your listeners who might not know what Encyclopedia Britannica is. Um, so it was hard. It was hard to express, that like I had decided I wanted to be an astrophysicist and now it was my driving force. And it took me through elementary school, high school, university, and I guess I never left university. I'm still there. Mhm.
so what made you overcome those challenges? Was it just the love of what you were doing, the love of learning, or were there other ways in which you kind of overcame those challenges of those challenges of social uh, difficulties and social interactions?
Yeah. I found, like a small, like two or three people that I really got along with. And I just kind of, hung out with them sometimes, but not all the time. I was really a person that kind of floated a little bit between groups, but just really I loved learning. And when I got to university for my undergraduate degree, it was less awkward because I felt like the people that were now my classmates were more people like me. And and so it was a lot easier to talk to them because like I guess they understood. I felt like they understood me a bit more. They were more like me, you know, neurologically perhaps. So that got a bit easier, but I still had, different groups of friends and I didn't have like one particular like niche where I fit in. So I did a double major in math and physics when I was an undergrad because I went to the university where my dad taught. He told us all very young, he's like, I have 7 children and I can't afford to pay for university for all of you. So I have, you get free tuition at my university. You can go there or you can pay for yourself to go somewhere else. So I was like, I will go to Carleton where you teach. So I did the double major in math and physics because there was no astrophysics program. And I wanted to be an astrophysicist. So I figured if I took the most difficult program that they had, that in graduate school, I should be okay. That it shouldn't take me too long to catch up with the different aspects of astronomy.
Mhm.
And I was right. It was extremely challenging, but so rewarding. And, it was also really challenging to be working up to 3 jobs at the same time because I moved out of, my parents' house and I like was living with my younger sister we had bills to pay, and didn't qualify for student loans. So I was working a lot. So that was really, really hard. But
Mm.
it was really my love of astrophysics that kept me going. And there were multiple times, in fact, at these jobs that I had. One in particular stands out where the human resources person comes by and says, like, hey, you're really good at this call center job. Like, why don't you just quit your degree and start working here full time? Like, you're going to end up here anyway.
Oh,
And I
wow.
was like, no, I'm going to be an astrophysicist. And he was like, yeah, sure.
Oh, wow.
Exactly.
That's,
Uh,
that's really,
yeah. But, also just, I think that, if you like, that might be true for a lot of people that are doing, different kinds of degrees or something. I don't know. But I
yeah,
was like, you obviously don't know who I am.
exactly.
I'm going to be an astrophysicist and you don't know it, but I know it. And there
And
were
that's
a few times where
amazing.
people were like, why are you doing this? Just like get a job. And I was like, no, I'm going to do black holes.
So was it maybe because of the community that you were in? Was it a community where there wasn't a lot of higher education? Or was it just maybe because of people's thoughts about women in science?
Oh, it's hard to say. So when I was in university, Ottawa is the capital of Canada and a big government town. And so a lot of people get undergraduate degrees and then go and work for the government. Um, so, and it's hard to fault people for, you know, seeing that path for me, right? That's really the path that a lot of people take.
Right.
So I just figured, like, oh, you think I'm someone else? Like, that's not me. And I I don't know where that very strong sense like of who I am, like the fact that I identified myself as an astrophysicist at 10 years old, it never occurred to me that that didn't happen in other people. And so when I saw other people, struggling to figure out what they wanted to do with their lives, like I could never understand. I was like, didn't you just choose something? Like just do the thing that you chose. Like I don't understand what the problem is, but this is I think where I start to be slightly divergent in terms of um, my thought processes and things like that. But I was able to like hang on to this thing, and instead of it being an impediment, I feel like it's really been a kind of superpower for
Mhm.
me that I was like, no, like this is who I am. And when I got to graduate school, I was almost thrown off track again, but then it kind of
Mhm.
like course corrected. I did a year of experimental work when I first got into my PhD program on this experiment that was looking for deviations from Newton's inverse square law. So, testing gravity on very small scales.
Mhm.
And deviations from this could come from things like string theory. So, at first, I thought that this is super cool. I'm testing string theory. This is awesome. But I really didn't get along with my supervisor. And after a year of butting heads, we parted ways in a spectacular, huge argument with the department chair. Um, and the group that ended up saying, like, hey, you know what? Like, you have really good theory skills. Like, come and work with us was the gravitational waves group. So I, kind of like went back to black holes. And it was a very natural fit. It worked out really well. And I'm actually very grateful for that year of experimental work. I can do all sorts of things now that I learned like in the machine shop, and I'm not afraid of the big machines, and I could create like instrumental pieces with my hands that I created a theoretical image of in a computer and then printed out the design and then made it. And I'd never done anything like that before, so it was extremely rewarding, especially when it worked, which took a long time. It takes a long time to get those things to work. So I also have a lot of respect for my colleagues that build things.
Mhm. Yeah, so it sounds very interesting in your transition into graduate school that, you know, you were drawn to black holes all through your years that you're growing up. But then it was almost kind of like now the black holes are drawing you in because you almost went off in a different path, but then
Hmm.
you ended up right back where you belonged. So
Yeah.
that's really great. So, um, now that we're kind of broaching the subject of black holes, could you tell us a bit about black holes themselves? Like, how are they defined? Maybe a little bit about types of black holes, and then maybe what you study with respect to black holes.
Yeah. So there's different kinds of black holes. Let's start off with the small ones. So we call them stellar mass black holes because they're a few times the mass of the sun. So those form in supernova explosions. And so you have very large stars that are something, like 30 times the mass of the sun. And those can undergo supernova explosions at the end of their lives. As a sidebar, our sun is never going to undergo a supernova. It's not big enough. There's not enough of that like oomph to create the supernova explosion. But more massive stars can go supernova. And when they do, they have this huge implosion explosion event. And the implosion crushes the matter and the core of the star, and it fuses protons and electrons into neutrons, and then it fuses the neutrons together. And the end product is something that we don't have physics to describe. It's some sort of, we call it a singularity
Mhm.
because mathematically that's what it is. But we have no idea what it looks like, if it really is this like tiny little point, or if it's this blob of quark gluon plasma, or like whatever it is, like we have no idea what that material at the center of a black hole is. So this, stellar core remnant that we call a black hole is not a hole at all. It's something in the middle. And the escape velocity of this is so large that light can't escape. So, what's escape velocity? So, if we're on the surface of the Earth, you can throw a ball up and it'll come back down again. But you have to throw a ball at about 11 kilometers per second for it to leave the orbit of the Earth, for it to, take off from the Earth. So, how far do you have to throw something, or how hard do you have to throw it for it to escape the gravitational pull?
Mhm.
The sun has an escape velocity of 611 kilometers per second. That's crazy fast. But the escape velocity of a black hole is the speed of light, and nothing can travel faster than the speed of light. And so if you imagine now that we're standing on this in the middle of this black hole on top of the singularity, whatever that means, this is just a
Mhm.
thought experiment. You can see light rays that might be going up towards the sky, or like up for you, but they would be bent and come back down, like water coming out of a water fountain and coming back down again, because the light can't escape from the black hole. And that's why there's this black sphere around it,
Mhm.
because the light just can't escape the gravitational pull of
Mhm.
whatever material is at the center of it.
Wow.
And so those are black holes. So they're not really black and they're not really holes, but that's what we call them. Supermassive black holes, which is what I work on, have a completely different formation channel. There
Oh.
hasn't been enough time yet in the history of the universe for all of the small black holes to find each other and merge together to form one of the supermassive black holes that I work on. So there are a billion solar masses. That means like one of those black holes would be the size of our entire solar system, right? Which is like bonkers large. So those supermassive black holes, we're not really sure exactly how they're created. One
Mm.
of the ideas is that there was this large gas cloud in the early universe that just directly collapsed into a supermassive black hole. That was, and this is maybe, 100,000, 10,000 solar masses, something like that. And then those ones found each other and started merging together.
Oh.
Maybe that's one way that they were formed, but the supermassive black holes that I work on like started big, and now they're even bigger, but they don't come from the stellar mass black holes, which is kind of cool.
It is interesting.
So back to your other question, so what do I work on? So I study supermassive black hole mergers. So these, we call them supermassive black hole seeds. The first supermassive black holes, however they got there, we're not really sure. Hopefully one day we'll figure it out. Maybe someone listening to this will figure it out because they also love black holes. That would be awesome.
Yeah.
Um, they find galaxies, the early galaxies, and then they co-evolve together, like how early cells got like, nuclei, and they kind of co-evolve together. The same thing happened with galaxies and black holes. They seeded galaxies with black holes. And then the galaxies started merging and the supermassive black holes started merging. And when supermassive black holes merge, they create gravitational waves, which are ripples in the fabric of space-time itself. And so these space-time ripples affect the distances between objects. So if you and I were sitting across the room from each other and a gravitational wave came down from the ceiling and into the floor, we would get closer together and then further away. Yeah. And then we would be like, expanded and look super thick and then contracted. And we would have this crazy like oscillation pattern go between us. But we wouldn't be moving. It's actually the fabric of space-time itself that's moving between us. And so this is what I look for, and this is what I model. I look for these gravitational wave signatures as they pass through our galaxy, and I also create models of what they should look like. So it's a lot of math and a lot of computers and a lot of fun.
It sounds fun. So, when you are looking at these gravitational waves, are you essentially studying kind of the what happens to the stars that are nearby these supermassive black holes?
We study the effect of pulsars, which are these intermediate phase, like they're neutron stars, so they're also stellar remnants. They're big balls of neutrons that are about 1.5 times the mass of the sun, and they spin around 100 times a second. Like if you put the sun and squished it to the size of Manhattan and put it in a blender, that's what one of these pulsars are. They spin around 100 times a second and send us regular flashes of radio waves. And those flashes are so regular that we can measure exactly when they should arrive. We measure when they do arrive. And the difference between those two things could signal the fact that a gravitational wave is transiting our galaxy, because it means that the pulsars got closer to us and then further away, and then closer and then further away. And
Interesting.
so, yeah. And so this is a way of using nature itself as this gravitational wave detector, because these pulsar pulses are so accurate. Any deviation and when those pulses arrive could signal the presence of, space-time itself being deformed.
Wow, very interesting. So, I know that there's a supermassive black hole at the center of our galaxy, the Milky Way. And my understanding is that there's supermassive black holes in the middle of other galaxies. Is this a typical feature of galaxies?
Absolutely. Yes. Most massive galaxies have supermassive black holes at the center. And I say most because we haven't looked at all of them, so we don't know for sure. But when we've looked, we found them. In fact, the Event Horizon Telescope collaboration in the last few years has actually taken pictures of our own supermassive black hole, Sagittarius A star, and a neighboring one, M87, that they call M87 star.
And so these supermassive black holes at the center of the galaxy, is it believed or known that they form in a similar way to these other supermassive black holes in the universe?
That's right. So our supermassive black holes were seeds at one point as well, and were smaller. And one of the really interesting things about these gravitational wave experiments now, like NanoGrav, which is the project that I work on, is that we can find these individual, like merging supermassive black hole signals. And that can tell us what the masses of the black holes were, from which we can infer what the host properties of the galaxies were, and then we can kind of work our way back in time as an additional check to see, does everything work the way that we think it should work. So like if I start at the beginning of the universe and then say, I have a small black hole and a small black hole, and by small I mean like maybe it's only 100,000 solar masses, right? Small, a baby supermassive black hole.
Mm.
And these galaxies merge, then I get this gravitational wave signal, and then these galaxies should merge and I get this gravitational wave signal, and then I build up mass, and then what's the end product? And that's really what we're looking at when we look nearby. We're looking at the end product of this cosmic merger history of all of these events. And so it's a nice check on how does the universe work? Does it work the way that we think it does?
Mhm.
And in the future, when we have other gravitational wave detectors in space, we'll be able to see these, baby supermassive black holes merging with each other or not. What if they're not there? Like, what if the signals aren't there? Then we'll have to rethink a whole bunch of stuff about the early universe. That would also be very cool. But
Yeah,
that's why we build these detectors, right? Because we have to go out and see it. It's not enough to just come up with fun theories, which I love to do. But I think one of the signatures of my theories is that they're all very testable.
right.
Because if they're not, then I'm not really sure what the point is.
Yes, of course. So the the seed supermassive black holes that are merging that you study, do you suspect that they will or eventually form into galaxies, or are they already part of galaxies that have collided? So I guess I'm curious about the relationship between a supermassive black hole and the galaxy that surrounds it.
Yeah, so the supermassive black holes that are local to us are the product of those seeds merging with other seeds and then over, the whole history of the universe becoming very big. And so that's the end product. And how galaxies and their black holes co-evolve is an open field of study. It's
Yeah.
something that everyone is very interested in right now in astronomy.
Oh,
Um, yeah,
yeah. So, this one is just kind of a curiosity question because I'm a little bit of a nerd about these things, but I'm also not an expert in
excellent.
them. um,
Excellent.
so this is about wormholes, which is somewhat related to black holes, but not exactly. Which were predicted in Einstein and by Einstein and Rosen with general
Hmm.
relativity. They're usually called Einstein-Rosen bridges. So, um, do
Very
you
good.
think that they can exist? And if so, how could they be detected? Do you think they could be detected in kind of a similar way as these black holes that are colliding and merging? These supermassive black holes that are colliding, with some type of change in space time or ripple in space time.
Right. What a great question. So I believe the answer to, so Einstein Rosen bridges, so they are wormholes. The theoretical calculations, I believed, allowed for one electron to pass through it. Like that, not people or spaceships.
Oh,
And one of my colleagues, Kip Thorne, has thought a lot about wormholes and over the last few years has become much more pessimistic about if they're real. And one of the reasons for his pessimism, because he used to be a big proponent, is the fact that to keep a wormhole open, you need a lot of negative energy, which probably comes from negative mass. And how can you do that? So this is either, we got too imaginative and created something that maybe can't work. But my gut feeling is that we need, a fresh set of eyes and fresh brains and people who are really excited about wormholes to figure it out. Because it seems to me like it's something that should be able to work. It seems to me like, space time is long and meandering and there's these hills and valleys. And why can't we make a tunnel through a hill? We do it all the time here.
good
I know
point.
that we need some sort of exotic material that has negative energy, but if you were to have told people 200 years ago that, gravity is the result of curvature of space-time, they would have laughed you out of the room. They're like, what does that even mean? So, when there was this paradigm shift with general relativity, it really allowed us to think about things in much more general ways. And something like that might be right around the corner. There might be some brilliant graduate student or young researcher who has a completely fresh and new perspective and can actually, figure out how to do this. I don't see, I mean, I want to believe. I want to believe that it's true. Doesn't mean that it is, but I want to believe it.
I do too. I think it would be really awesome, and it would just be awesome to discover whatever it is that would actually keep it open. So this whatever this exotic matter would be, or maybe some
Hmm.
other property of gravity that we don't understand. I do have a question from our previous guest, Dr. Carlotta Berry, and so she asks, "What problems in your current work keep you up at night?"
I guess I have two answers. I have a scientific answer and a like reality answer. The let's see. The the scientific answer is, what keeps me up is like, what am I missing? What is there something that I'm missing? Have I left out something? Um, like did I dot all my I's and cross all my T's? It's very much, what am I missing? What's happening? Um, but in terms of like my work, like the bouts of creativity just kind of like happen and I can't control it and I've basically stopped worrying about it because it just it's great. It happens and it happens when it happens, but I can't force it to happen. And I just have a notebook with my ideas in it and work through them with my students, and that's wonderful. In fact, it's the best part of my job is mentoring my PhD students, and I've had very talented undergraduates as well. It's just such a pleasure to work with them. The reality of what keeps me up at night is how am I going to pay for all of this? And I need to get grants and I need to write big grants and I need to spend a month, 6 weeks of my life putting together this massive document of all of my research plans for 5 years and then submit it to the ether. And then some, board gets together and decides if my work is worthy or not. And then I get money or I don't get money. And then if I don't get money, then how do I pay my students? And I care so much about my students. I want them to all be okay. I don't want them to have to um, you know, look and find their own sources of funding. It was so difficult for me as a student to have to work so much that I really would like for them to be able to focus on their research and not worry about things like that. So to the best of my ability, I do that. But yeah, so those are there's a scientific answer and then there's like a for real answer.
Yes, I mean, and that's also a good thing to kind of just share, one for those who may be thinking about the path of academia, that is a big challenge in academia, and it can be very, like you said, time consuming and very difficult process. And sometimes you're just like, why can't I just do my work? Why can't I
Right,
just do my research?
exactly. Yeah.
So it's good to share the realities of it, and that it still is something that you're passionate about regardless. So
Hmm.
I hope that all of your grant work goes really, really well and you can get lots of money.
Thank you. Thank you. My students will be really happy if I can make it rain.
So just to kind of begin to wrap up, I just have a few kind of random questions to ask you.
Hmm.
So this question is inspired by the podcast, The Diary of a CEO. And I always hope that he will be okay that I that I use this question. But what question would you like us to ask the next person that we interview?
What inspires you?
What inspires you? Very good.
Hmm. I think it's really interesting, right? Like what inspires different people and then how they choose to answer the question, I think is also really interesting because it's kind of
Definitely.
open-ended. Yeah.
Yeah, definitely.
What inspires you?
Oh, what inspires me?
Yeah.
I am inspired by a lot of different things. I'm a very curious person. Um,
Hmm.
and so I guess I'm also inspired by other curious people, like people who like kind of like yourself, who just find something so interesting and just commit yourself to understanding it and learning more about it and sharing that knowledge with others is really inspiring to me. So I'm just really curious. I like to learn, and I like to learn from other people. And I think that kind of that process of learning and conversation is all really inspiring to me.
Oh, fantastic. Thank you.
Um, who else would you recommend that we interview or speak to?
I think it would be great for you to interview Priya Natarajan. She's the chair of the astronomy department at Yale, and just such an interesting person. She's brilliant and really funny and very generous, very kind person. I think that she'd be great to interview. Um, Professor Jenny Green at Princeton University is another one of my collaborators, and she's also just so sharp. Um, like she just asks the best, most penetrating questions, and I really admired that in her. And Julie Comerford, who's also a professor at CU Boulder, she does a lot of work in observing galaxies and active galactic nuclei and lots of things with supermassive black holes. And again, just like so smart and so kind and so generous and extremely well read. So yeah, I would love for you to interview her as well.
Great. Thank you so much. So
Yeah,
just a
you're
couple
welcome.
more questions. So if you could write a book about a well-known person in STEAM, so science, technology, engineering, arts, and mathematics, who would it be about? Maybe a children's book, for example.
It would be fun to write a children's book about Einstein, but Einstein is so overkill, right? Everyone has written books about Einstein and like general relativity for babies and, black holes for babies, that kind of thing. That could be really fun to do as well. Like just because
Mm.
other people have done it doesn't mean that I couldn't do it. But
Is there
a
something unique
particular
about Einstein that you haven't seen, produced in any kind of a book?
Sure. I would love for there to be a book about Einstein is wrong because there was lots of times where he was wrong, but he has really good press even though he's dead and every headline is always Einstein is right. Einstein passed another test. But the Nobel Prize is given for entanglement and Einstein didn't believe in entanglement. He called it, spooky action at a distance and this can't be right. But he was wrong because it's real and they proved it. But the
Yep.
headlines weren't Einstein is wrong. So he's they should have been. So
Mm.
he's got really good. Actually think it would be fun to have a book called like When Einstein Was Wrong and go through all the things that he was wrong about
Yeah,
because he was a brilliant, brilliant man, of course. But I just think that that would be a fun take on it.
it would definitely be a fun take on it. That's that's really funny. So would you like to tell our audience where they can find you and learn more about you and your work?
Yes, so I have a website which is chiaramingarelli.com. You can visit that to see what I'm up to, what my work is. And I'd also like everyone to check out the nanograv.org website. On Thursday, June 29th, we will have released a suite of papers that talk about evidence for a gravitational wave background, which comes from the cosmic merger history of supermassive black holes. So definitely check that out.
Very exciting. We'll definitely make sure that it's linked and everybody knows about this excellent announcement and the great work that you're doing. So, thank you so much for making time to speak with me today. Is just it's really fascinating to hear your story from just staring out at the night sky and just how that inspired you to then move towards astrophysics and just those little moments in our childhood that seem so mundane but that they can just direct the whole course of your life. So thank you for sharing that with us. And thank you for kind of going with my geekiness on wormholes a bit.
Oh my gosh, the wormholes was my favorite part. I love your questions about wormholes. Thank you so much. This was
Thank
so
you.
much fun.
Yes, this was so much fun. And I hope that you have a great day. And thank you
Thank
for
you.
joining.
You too. Thank you so much.
Thanks.
Bye.
Thank you for joining us on Origins with myself, Dr. Natasha Wilson. We hope that you will join us again. You can find us at www.originsconvo.com, as well as on Twitter and Instagram using the handle at OriginsConvo. Please join our Substack at originsconvo.substack.com, where we will post interviews and other interesting content for both free and paid subscribers.